everybody. So, so these are, this conference has two purposes: optical design of soft matter, and also to celebrate the many women that have made so many contributions to soft matter. And I would like to here emphasize the women which have been in my group, which is this part here. So Elizabeth Macias and Shunun Jia, and also collaborators like Hong Xiaogu and the Chinese Academy, and also some experimentalists, and also other experimentalists which I had the pleasure to work. Also, I would like to make some advertisement. I am the associate editor of computational material science, and here we would like to love to get more papers which are in this area of liquid crystals and topological defects and things like that. We are not getting as many as we would like, so I'm just making here a pitch that you should submit to this journal. It's beautiful. It has a respectable impact parameter, and I hope to see more papers. So with that, let me just go. I will talk about nanoparticles, also called nanocrystals. So basically what we have is we have some discrete number of atoms, like 2,000, 4,000, 10,000. And in a way, it's the minimal amount of matter that makes a material, in the sense that these type of small materials have all the macroscopic properties of real materials, like plasmonic bands and conductivity and things like that. They are typically in the nanoscale. In order to make interesting materials with them, you typically have to functionalize. So what that means is that you have to attach some typically organic molecules that make them soluble and stable in a solution, and then you can consider putting them into interesting materials that perform interesting functions. Here you have an example. This is gold, but there are semiconductors, there are insulators, there are all sorts of materials or nanoparticles or nanocrystals. Nanoparticles, nanocrystals basically is the same word, different context. And here is what it looks with a functionalized nanocrystal with, in this particular case, hydrocarbon chains. These are some of the cool properties that nanocrystals have. Those are different size nanoparticles. They emit a different color, so the fluorescence actually changes with the size, so you can get different colors by just changing the size of the nanocrystal. One of the goals in this field has long been to make a superstructure of nanocrystals, so making a lattice not just of atoms, but a lattice of nanocrystals, such that the ligands, which in this case are hydrocarbons and are insulators, become conductors. So the idea is that you start with some nanocrystal, ideally a semiconducting one. You have the ability to put some inorganic ligands that are conductors, and then you make a lattice of these things, and that, it has been one of the holy grails of this field. But today we are going to talk about interesting materials, and the first thing that we would like to understand is how these nanocrystals bond. So we know that if we have atoms, we have different types of bonding: nonpolar, polar, and ionic bonds. Those are how atoms or molecules bond. When it comes to nanocrystals, it becomes a little more complicated, because in that particular case, the ligands is what determines how they will bond. So the idea is that you have a nanocrystal, you put some ligands here, and then you put them in solution, and then you do something to the solution, you change the conditions of the solution, you evaporate the solvent, you do many things, and then, or you change the temperature, and then these things start to bond. And this would be one example. And in this case, the role that the electrons play now is played by the ligands, which actually determine the bonding. And you can also have polar covalent bonds. So for example, you could have nanoparticles with DNA functionalized such that the end parts of the DNA have complementary strands, and in that case, that would be a situation where these complementary strands are recognized, and in this way, you build a superstructure. And there is also an equivalent of what would be a ionic bond, in which what you have here is that these particles attract each other, but they do not really deform their shell. There is no hybridization between the ligands. So what I'm trying to tell you here is that the role that the electrons play in bonding atoms and molecules in the world of nanoparticles or nanocrystals is played by the ligands. So the ligands determine what type of bonding and what they will make. So what has been accomplished? A lot has been accomplished. So the idea is, for example, how to make crystals out of nanoparticles. So instead of having, for example, here would be a covalent crystal of diamond, so each of them is a carbon atom, and then you form diamond. What you would like to do is the same thing, but instead of having here an atom, having just a nanocrystal. And here are examples of a binary type of nanocrystals. Here you have two types of nanocrystals, and they form all these structures which are known by the equivalent isostructure of the inorganic type. So for example, here, for example, we have sodium chloride, which is table salt, and then table salt. Here you have two types of nanocrystals that are forming a structure which is table salt. And there are many more. I mean, one of my favorites is, for example, sodium zinc 13, which is this one here, which has a unit cell which includes 112 nanocrystals. So it's a huge unit cell. And you can also form quasicrystals as well. So here you have an example of a quasicrystal that you can form with these type of things. So the idea is that we have, and this is just one of the many examples of the type of structures that you make. So the question is, you have this huge parameter space, you have all these sorts of nanocrystals, they can be functionalized with all sorts of molecules, and the idea is how you combine them and you make materials that are interesting, either because they have an interesting structure or because they have some functional property that is highly desirable. So the idea is that, well, I mean, you have all these type of things, and then you have to functionalize them, and by effect of basically KVTs, typically you would go to something that looks like a mess, but what you would like also is to form an order structure, like for example a nanoTaj Mahal, and that would be what is a successful structure. So the idea is that you have all these many molecules, ligands, etc., and what you want is to design which of those will give you interesting structures. Not only that, this is just just one type of structure, but what you would like is to have a city of structures so that you can put a semiconductor nanoparticle here, or a conductor here, or an insulator, or a conductor, and then make them do different functionalities and have all sorts of complex structures that you can design at will. So this is actually the goal that we have in our group, and this is what I'm going to talk from now on. So this is something we've been doing for quite some time. We started by considering nanoparticles that are functionalized with DNA, and this was based to two experiments that were published at the same time by Mirkin Group and Oleg Gang, and we've published quite a lot of work in that area. And then we continued with looking at what happens when you have hydrocarbons and how these nanocrystals can be assembled into ordered structures, and this is something we've been working a lot in the last few years. And we also have our own experiments with my collaborators at the Ames lab, where we have water-soluble polymers, also diethyl linkers, and more recently we have another one which is by interpolymer complexation. So the idea is that you have two types of nanocrystals, and through a third type of agent, in this case polyacrylic acid, you can direct how these things self-assemble, and this is a paper that we recently published to the Journal of Physical Chemistry C. I mean, we tried to have it in a higher order impact, but the editors kept rejecting our paper. But I'm really, really proud of this paper, even though we couldn't make it into a higher impact journal, so I will advertise it, because I really think that it was one of these many situations that all of us have experienced, where the editor rejects to send it to referee. Anyway, so I'm going to talk only about this today. I have many results on these other things, and if you are interested, I will be more than happy to talk about. So this is actually the subject that I'll be describing, what happens with superlattices of hydrocarbon cap ligands. The idea here, this is what the experiment does. So you have two types of nanocrystals, and they are functionalized with hydrocarbons, with alkyl thiolates, and you put them in solvent, on something that looks like that. Then you gradually evaporate the solvent, and then at the end of the evaporation process, you are left with this particular structure. In this case, is sodium zinc 13, which I already anticipated is one of my favorites. So the question is now, how can we predict what type of structure we'll find here, and how can we use theory to guide the design of all these materials? And that's actually what we would like to accomplish. So the first idea is just to assume that these type of crystals with the hydrocarbons here you can model as a hard sphere. So that's the first approach one can think of. In that case, so the combined system that consists of the nanocrystal plus the hydrocarbons are modeled as a hard sphere. And this is a hard sphere. One I should think is that this is actually a short surfactant. So this is typically, for example, nonane or hexadecanethiol or stearate. What means is that here we have 9, 12, 18 carbons. The Kuhn length is about 6 carbons. So here you don't have a polymer. This is not a polymer system, okay? So that all the descriptions that you know in terms of polymers, in terms of brushes and things like that, they do not apply here. You cannot use those because it's not the validity. So you have to come up with some other description. So the way you can do it is you can define L as the maximum hydrocarbon length. So here you have, so that would be what is the length of the hydrocarbon maximally stretched. And then you can define these dimensionless quantities. Lambda, which is L divided by the radius A. Radius A is the radius of the core. And then tau would be the dimensionless radius of the sphere. So that would be the equivalent hard sphere radius that this nanocrystal would have. And the value for tau is given by this expression, which was derived in this paper many years ago. And that gives you what is the hard sphere equivalent radius for this object. You have to note that in principle, it's not clear that we can describe this object as a hard sphere because, I mean, in principle, you would think that these hydrocarbons are compressible, yeah? So a description in terms of hard sphere, in principle, I mean, you would think it will not work. But let's go with that. So the idea is that we are going to consider these things as Dillier balls, very hard spheres. And let's see how far can we go. Well, so basically that becomes a packing problem. And in that particular case, what we know is that packing problems is something like that. So the typical quantity that you would measure is how effective is this structure in terms of packing. So for example, for a square lattice, the total area of the square will be 2r. The occupied area will be pi r squared. So the total amount of space that it is actually occupied by matter would come to 0.78, which is the packing fraction of a square lattice. In 3D, we have these other structures that we all know, like FCC with 0.74 and BCC and simple cubic and many more structures that one can consider. But the thing is, here we are considering binary systems. And one thing that we can clearly tell is that with binary systems, you can be more effective in terms of packing because you can always imagine that you can put smaller spheres in the interstitials and in this way enhance the packing. In fact, the packing will be a function of the ratio between these big and the small spheres, which is a value that we call gamma. And in general, depending on the ratio of gamma, you will have a maximum packing that will depend. So when you go to 3 dimensions, this is what you get. These are different lattice structures, binary lattice structures that you can have. And you can see here that there are many cases where you overcome the maximum packing fraction of FCC, or the maximum packing fraction of any single component lattice. And you see here that, that you can overcome this. So here you have. And then why this is relevant? Well, because in an experiment, what you can do is you can put these things in a 2-dimensional lattice. From the lattice constant, you assign the hard sphere radius. Okay, so that is something you can do in an experiment. And then what you can do is say, okay, so if I put this particle which has this particular radius and this other particle which has this other particular radius, so it has this value of gamma, what structure I will find? And then you make a plot where you take this packing fraction. Then what you see is that there is a correlation between the maximum packing fraction and where the lattices are. So for example, this is aluminum boron 2, and you can see here that you have that the experiments, which are right there, are at the maximum of the packing fraction. So there is a correlation, and that shows that the description in terms of hard spheres is not as bad as one may have thought. Actually, it's pretty good. However, it's far from perfect, because for example, if I look in this particular case, the magnesium zinc 2, I see that if I were to believe that, that means that for this particular point, for this particular experimental point, I would have a packing fraction which is only 0.5. It's hard to imagine that such a low packing fraction would be a stable structure. But on the other hand, you know, there are some other experiments that seem to work. So what this is telling you is that there is a clear correlation, but it is actually very imperfect. So the question is, how do we go about next? Well, one thing that you may think, as we anticipated, is that you could always consider a situation where instead of going from hard spheres, you go to something which looks like more compressible, like tennis. You can do that. You can consider a potential which is a little more flexible than hard spheres. And when you do that, you know, you start getting that this, I mean, this is the range of the thermodynamic equilibrium structure, and you get that they extend a little over what would be the hard sphere stability. The problem is that in this particular case, you start adding new parameters to the system, and it becomes a little bit questionable to what extent are you going to start tuning the parameters. Also, there are other problems, like for example, these are experiments. So for this particular phase, which is called lithium-3 bismuth, this is what the hard sphere packing fraction is, and this is where the experiments are. And this is something that no matter how much you stretch your potentials, if you are an honest calculation, you are never going to be able to just bring this potential to be any potential that you can reasonably consider to make it to make up for this huge change. So, I mean, basically, you can improve a few things with softer potentials, but if you are doing an honest calculation at the end, it's not going to work. So you have to go to something else. So what else you can do? Well, one thing that is clear is that these nanocrystals sometimes behave as hard spheres, sometimes they behave as softer spheres, but it's never quite, it's hard to tell what is going on here. And this is what we have to do, is we have a theory, we have to do a theory of ligands. So here's where we are. So we have modeled the nanocrystals as hard spheres, and this is the diameter that they have based on lambda, which is this parameter. You can always consider a situation which was considered before in 2009, where instead of just having these hard sphere radius, the spheres are able to deform into this cone, and that gives rise to this other model, where in this particular case you can see that the particles are closer by 1/3 of the hard sphere packing fraction. So for example, if particles were in an FCC lattice, that would bring them 0.724 to the 1/3 closer than OPM. That's what would be. So this is another alternative model. Now the question is, we can here starting to look and study all sorts of models, but at the end of the day, it is the experiment what determines what happens. And these are the results of the experiment. It's a very clever experiment that was done, where they took a two-dimensional system and they looked particles that have coordination 3, the green ones, coordination 4, the red ones, coordination 5, the blue ones, and then there is coordination 6 and coordination 12 by looking at an FCC lattice. And what they see is that separation between nanocrystals, starts coinciding with this model for coordination 3, and then starts moving up and eventually reaches the result of the hard spheres. So what you see here is that you start going from something that is clearly beyond hard spheres, but eventually as the coordination raises, you reach that value, which is the hard sphere value. And this is actually an experiment. So there is no, I mean, other than these curves, which is the OCM, this one, and the hard sphere, which is that one, that's as far as the experiment went. So now what do we do next? Well, what do we notice is that we consider a situation where we have a mix of a hard sphere and one which is highly deformable like this way. So this is what we consider. And basically what we are doing here is that we are considering that this is a point and there is another point that reaches to that end, and that defines a three-dimensional vector that points out of the center of the sphere. And in a way what we have here is a mapping from one dimension, a unit vector to the sphere. So what we have is a Skyrmion. So basically we can consider this as Skyrmions if one can consider that this ligand somehow can be represented by a rigid rod. Let's go with that. Yeah. So then what will happen here is that this is a Skyrmion, and no matter what you do, it will always be Skyrmion, and the charge will be -1. So that is not going to change. But what you can change is you can change what are actually the directions of the projection of this three-dimensional vector onto the surface of the sphere. And when you do that, you realize that in a situation like that, if you just turn this around, you will be forming a vortex. So the idea is that when you have an OCM type deformation, you generate a vortex. Then you can always consider naively the topological theorem that tells you that you can only have two vortices on the sphere. But in reality, those are not truly topological defects, because this is a three-dimensional vector, so you can always have a situation where a neutral line where the defect has a zero projection and escapes through the third dimension. So in principle, in this model, you can have any number of vortices you want. However, what we claim is that the vortices have a huge energetic cost, and this would be a situation. But what we claim, and this is actually what we call the OTM model, is that for you can only have up to 6 vortices, and at that moment it becomes too costly to create more of these deformations. So basically, this is the assumption, and the other thing is that these vortices are consistent with the minimum separation that they can have. So in a way, these vortices behave like hybridized atomic orbitals. That's what they behave like. So basically what we've gone is we've gone with the billiard, we've gone to the tennis, and now what we do is we have these situations where in some cases, in some specific situations that depends on the coordination, you can have these vortices, and then out of these vortices, you can have these large deformations, and that is how you overcome the limitations that give you the hard sphere model. So let's see how this works. Let me take a very common lattice, which is magnesium zinc 2. And this lattice is here, so this is the packing fraction. You see that it has a maximum at around square root of 2/3. And this is the maximum packing fraction, and then any other direction, the packing fraction goes down very quickly. So we start at gamma critical, and this is the structure. So you have here the big red balls are here. They are forming a diamond lattice, and the blue ones are forming a pyrochlore. Yeah, as we assumed, there can only be deformations for these ones because those have coordination 4. Those coordination 6, as according to our assumptions, they cannot form vortices. They have to behave like hard spheres. So the only ones that can actually behave as non-hard spheres are these ones. Yeah. So with that, this is the type of vortex structure that you have on the nanoparticle. So you have what we call a tetrahedral type of structure, and doing some math that, I mean, you can review, you get to the separation that this new assumption makes over the separation that you will have with the hard sphere. So this is actually the formula. And now you can go and compare with the experiment, because this is the magnesium zinc 2, this is electron microscopy images. You can plot the lattice constants, and then you can also tell what is the actual lattice constant. So what are we doing here? Well, we are considering, first of all, this branch. This is magnesium zinc 2. The first thing we notice is that the experiments are only on the left side of the curve. What that means is that you cannot have, I mean, if we had vortices for the small particles, then we would have experiments on this side, but there are none. So that is a first qualitative thing that is in agreement with our observation. Then we can also go and calculate what is the packing fraction. Now, because we have this ability to form vortices, this is the hard-sphere packing fraction, and now we develop this new branch where the packing fraction becomes higher than the hard-sphere one, and therefore what we see is that we have a prediction for what would be the packing fraction if this packing fraction is measured on an actual experiment. So what we see here is that all these very low packing fraction things that would be predicted if things were hard spheres are replaced by these other ones that are possible because there are vortices that allow this higher packing fraction and closer approximation. So let's look a little bit at the experiment. So this is actually an experiment result. So this is what you see here is you have the hard sphere prediction. So if the particles were hard spheres, you would have that this would be the prediction. This is what actually the experiment gives us. And now when we put the results for the OTM model that we just developed, we realize that without any fitting parameters, we are able to nail each and every one of the separations for this particular system. And there is one case which we couldn't predict, but actually has to do with a different type of bonding that occurs. And for example, here you had the lithium-3 bismuth that I mentioned before. Now it turns out that when you do the right thing, here you see that there is a new branch, and the experiments, once again, fall perfectly within what we predicted. So this description of nanocrystals as soft skyrmions and vortex textures as appearing in the particular circumstance we described without any fitting parameter or any free parameter, we are able to explain all experimental systems. I will skip that because I would really like to talk about. So those are, for example, what we have. So here you have the different type of packing fractions. So for example, here what we have is we have a structure of vortices that corresponds to the tetrahedral one. This is what the magnesium zinc 2 has. This is the equatorial one where you have vortices along the equator, and that's what the gold copper 3 has. And this is the BCC AB6, which is another type of very common structure, which has also this particular type of structure. And this is sodium zinc 13, which is another part. And this one doesn't have any OTM branch, so this is actually an example of ionic. This is actually the only system where everything behaves as quasi hard spheres. So that's actually a situation where we have hard spheres model. There are these less common orbitals that I'm not going to talk, but those are the actual ligand textures that define how these nanocrystals bond and how they form to these superlattices. So what you can do now is you can use these things to combine them and try to find new structures, and this is something that I will not discuss here. But basically, what we've shown is that, for example, we had a talk this morning about nanocrystals or colloids with valence. What we have here is the ability to spontaneously generate valence. So for example, we have 3, 4, or 5-fold. This is 3-fold. This is 4-fold. So we are able, these nanocrystals have the ability to spontaneously generate valence and have, for example, a 4-fold or a 5-fold or a 3-fold, depending on the environment. So even though they are isotropical objects, by the formation of vortices, they break that degeneracy and they are able to form valence. I would like to put some more geometry because I love geometry, and here's the right audience to do that. So we all know this is a perfect lattice, this is a disclination, positive disclination, negative disclination, dislocation. We all know that we can have a perfectly 5-fold lattice if we consider an icosahedron, so each point here is all of them 5-fold, and the price we pay is that we go from 2 dimensions to 3 dimensions. So if we explore the 3rd dimension, we can have a lattice where each point is 5 coordinated, okay? We could try to do, this is buckling and this is the curving. If we try to do the same thing in 3 dimensions, we cannot do it because actually when we start putting tetrahedra, perfect tetrahedra, there is this small gap, and that prevents us from tiling the entire space with tetrahedra. Now, if we go to a 4th dimension, Here we have it by my good friend Henry Segerman. This is actually the 335 polytope that it is stereographically projected in 3 dimensions. You can check that this is actually made of perfect tetrahedron, that if we were able to live in 4 dimensions, we would see as perfectly equilateral. Now, one thing that you can do is you can decurve by disclinations. And if you just use these type of disclinations, you get this particular structure with magnesium zinc 2, and for those familiar, that is a Frank-Casper phase. What happens is that the 335 polytope has the ability to have other types of disclinations that are allowed by symmetry, and when you start decurving using those, you start getting all the superlattices that we have seen before. In other words, all the superlattices that have been found experimentally, and that includes also DNA, which I haven't talked, are also the not Frank-Casper phases, but what we call quasi-Frank-Casper phases, in the sense that they are combinations of these disclinations, of these types. So here you have, for example, aluminum boron 2, which I mentioned before, sodium zinc 13, and so on. Sodium zinc 13 is my favorite because it's actually done of -2 pi 3 disclinations. So with that, I have to, well, I would say that this 335 is actually the mother of all superlattices. All superlattices come of this 335 polytope. It's really an extraordinary result. Basically, what it's telling you is that all superlattices that have found come from patching tetrahedra structures. So, I mean, I can do a little more things. I would like to mention these experiments that have recently appeared, where basically show, for example, among many other things, that all this is the fraction of icosahedral, and this is the type of fragments they have. So we see that all they have the icosahedral, they already form fragments, showing that there is this strong tendency towards forming icosahedra, and there are many more. Actually, in the 5 minutes I have, I do have 5 minutes, yeah? So I would like to talk about, we do simulations, and I call simulations the art of convincing experimentalists, because what happens is that everything that I told you today, the experimentalists don't believe a word. And it's really sad, because you tell them, you show them, look, this is the experiment, this is what I have. And some of them believe you, but most of them, they don't believe you because they don't know what you put into the model, and you tell, no, I didn't put anything, but they still don't believe you. So I'm forced to do all atom molecular dynamics simulations, because when they see the molecules, then they say, oh yeah, that's true. So that's why we do simulations. And we've done simulations for quite a long time. We have developed different codes. We have WHO-DLT, which is a new code that we've developed, which haven't shared with anyone. But for example, using that code, we can calculate free energies. We can calculate all these simulations that have to do with nanoparticles. We can calculate all the OTM models are implemented. Everything is implemented there. And as an application, for example, we've discovered that the traditional Energon system has a low temperature HCP phase. So people, I mean, this is something that when I got this result, I thought that for sure there would be someone that had done it before, and I thought there will be one of these papers in the 60s by some Russian that had already predicted that this was the low temperature phase, or then there would be a paper by Dan Frankel that he already proved it. But I actually met Dan Frankel a few years ago, and he told me he didn't know that result. So that makes me think that, yes, this is an original result. So basically the Energon system has an HCP low temperature phase with a phase diagram that looks something like that. Anyway, but that's not what I wanted to talk. Those are the simulations that we do. We've been developing methods to do these things. So one thing that we can compute is, for example, we can compute the potential of mean force between 2 nanocrystals. This is what the free energy looks. This is what the energy and the entropy looks. So you can see that there is a huge energy entropy cancellation, because the free energy is much smaller in magnitude than the entropy or the energy separately. And the other thing we can do is we can turn this around, and here you have the vortices that we predict. So that's actually the type of things that experimentalists believe, because they see it with their eyes. But, well, you know. We have also done other type of calculations. For example, we have seen that as you take a 6-fold and you start meeting together, we can characterize many body effects, that effects that do not come out by 2-body interactions. So here you have the difference between the 2-body and the actual many-body effects. So here you have repulsive, always repulsive many-body effects. So we can actually characterize those. I mean, there are many more things we can do. We can also talk about vortex coalescence. And here, remember that plot that we had before? we have the analytical result, but we also can get the same thing by numerical experiments. So you can here you see that, I mean, this is kind of the things that hopefully convince experimentalists that what we have is actually a true theory. And for example, we have here how the many body effects appear as a result of vortex coalescence, how the vortex, when they start interacting with each other, that's when many body effects take place. We also can show by doing, starting with an FCC type unit cell, we approach them together and then they eventually deform into forming an icosahedral type structure, which is exactly what we need to do to show that, showing that as you start getting together, well, I mean, the diamond or the icosahedral structure is the one that it is the lowest free energy, and indeed we can see that. And we can also see that, for example, if we have a tetrahedron, we see that as we approach here, you have 4 vortices, 1, 2, 3, and another behind. But when we have an icosahedron, this has coordination 12, the 5 has vortices, but then the coordination 12 doesn't have vortices, and this is exactly the type of results that we had predicted in our theory. Now we see it with numerical simulations. So those are important. That we have also calculated the free energy of superlattices. As I say, I mean, you know, here you have, for example, for a BCC or for an FCC, we basically calculate the pressure, we do some tricks, and eventually we get the free energy. The minimum of the free energy is the equilibrium lattice constant. And one thing that we also see here, again, there is a huge entropy, enthalpy cancellation. The free energy is much smaller than the magnitude of the energy or the entropy. We also can see that although here it's not very convincing because it's not within the errors that we have in our calculation, that the BCC for long enough chains has lower free energy than the FCC. But again, I mean, if you look at the numbers, they are not outside the error, the margin of error of our calculation. The other thing is that there are no vortices because this is 12 coordinated. This is actually 8, but in reality it's more like 14 coordinated because the nearest neighbors see each other, next to nearest neighbors see each other. And you can see here that this is the quasi-sphere radius. You see that the minimum occurs exactly at the quasi-sphere radius. So meaning that both in FCC and BCC, the nanocrystals behave as hard spheres, which is what we expect because the coordination is actually 12. So here you can also see that a combination of all the experiments that we could find in the literature, and you see that for small lambda, for short chains, it's FCC, for large chains, it's BCC, and there is an FCC transition, and my time is up, so I'm going to go to the conclusions. I'm going to go to the conclusions. Here I have the conclusions. I'm not going to talk about DNA, or I'm not going to talk about polymer ones and so on. Basically,
2 minutes.
Well, that's okay. And people are tired, they want to go home. So the thing is, we've started with a hard sphere model. We just made a little bit of a tennis deformation, some compressible spheres. I mean, that fixed some things, but created another new type of problem. So, I mean, that is not, but at the end, what really makes it is this ability of being a hard sphere that can actually have vortices. This is what really truly describes what really happens in those systems. So sometimes they are hard spheres, sometimes they are flexible, sometimes they are vortices, but it is always described by OTM. And this is what the OTM is. So you basically have the hard sphere one here, and then you get replaced by this new branch, and that's where the experiments are, and we had perfect agreement. We took, I mean, there are over 200 experiments that we were able to find in the literature, and all of them are consistent with this description. And the description of this, for short enough chains, the description of nanocrystals works as soft skyrmions. As the chains get longer, then it becomes a polymer, and the standard polymer description with brushes and so on is what would work. There is an intermediate regime that we are looking into to see how you transition from one description to the other. And there are these vortices that we have shown, and there is a strong tendency towards icosahedral order, and basically all of these have I should say more tetrahedral order. This is what it is, but in the literature states icosahedral, but what it is actually tetrahedral. And all the superlattices that have found experimentally can be described as quasi-Frank-Casper phases. Not Frank-Casper because we need more general declinations, but that's what they are. And there are intrinsic structure reflecting topological and geometrical connections. And the optimal design principles, and this was one of the goals of this conference, is basically twofold: high packing fraction allowed by the vortices, and tetrahedral, which is the real word, icosahedral order. So this is the tendency that you have to use in order to design these nanoparticle superlattices. And here I have some propaganda that you can read. So with that, I'll finish here.
So thank you very much. So I see the next speaker, I guess.
Okay.
In place. But we can have one question maybe while they change over. So the last talk is going to be a 20-minute talk, and it's by Shayandev Senior. Sorry for my pronunciation, from Harvard University.
So there is a question.
So if there is a yes,
So
at the end.
what you say works for these short 6 carbons and so on. So when does it break down? Very large N?
Well, I mean, the thing is, there are polystyrene systems. That's actually the ones that I mentioned to you with Hongsha. We are looking at them. And those have been done with increasingly, I mean, those include like, the most we can have is 18 hydrocarbon chains. This is definitely not a polymer. But with polystyrene, they are able to go to actually having 30 Kuhn lengths, or 10 Kuhn lengths.
Your theorems hold?
Well, I mean, looking at the experiments, we can describe the lattice constant they report with the thing, but there are errors that appear there. So they are already, when you go to sufficiently long, you start getting errors, yeah? But they still qualitatively work. And the question is that for sure at some point they will break down as you make the polymer longer and longer. And that's something that we are currently looking at.
We have the drinks afterwards, so I think the IT people will go home at 5 o'clock, so I want to finish more or less at 5 o'clock and not to steal too much time.